I'm Siddharth, and I'm from Mission San Jose High School in Mr. Umit's class, studying linear algebra in semester 2. Today, in my lecture, I'll be doing my final project on eigenvectors and eigenvalues and their use in the PageRank algorithm, which has been used in many different search algorithms, most notably Google, in order to find pages that are most relevant. But I'll get into that later. So the first thing is to first explain what eigenvectors and eigenvalues are. I'm assuming you have a basic knowledge of vectors because this is from Unit 5, so I can't explain absolutely everything. But first, the basic concept behind eigenvectors and eigenvalues is that eigenvectors is a vector x such that when you multiply like x by a linear transformation like A, you get x times a certain constant. So like what does that actually mean, right? So for example, let's say we have a vector that is 1, 1, right? And we are trying to multiply it by our linear transformation, which is A right here. That is this vector 2, 6, 4, 4. Now when we do the math for this, we do some vector multiplication, right? So it is 2 plus 6 and 4 plus 4. And this would give us 8 plus, and this would give us 8 and 8 in the corresponding vector, right? And we notice something over here. This vector x, which is what we started with, times 8 is our answer. So in this case, our eigenvector is our vector x, which is 1, 1. And our eigenvalue is the value 8, because 8 times 1, 1 is ax. So lambda is the eigenvalue, and x is any vector such that when you multiply by a, you get lambda times itself. Now, this is used in lots of different fields of linear algebra, lots of different fields outside of linear algebra as well. And it is extremely useful because there's lots of different linear transformations, and sometimes we want to figure out what is actually on the coordinate plane. So one of these examples is websites, right? Now, websites are all connected together. For example, I created this diagram on Google Sheets, right? So like you might have one website, another website, and 4 websites total on the web, right? This is my example. And on each website, it might link other websites, and it might have some words on it. Now, previously, beforehand, you would have to go and order sites based on how many like of the word is on the site. So, for example, let's say I'm making the first Google, right? And I'm trying to make sure that when someone searches up, for example, cool dogs, right? What sites should show up? And I have a bunch of like list of websites. In order to do that, we need to first figure out like which sites are important. And instead of just seeing which sites have the most like cool dog text, we can figure out which sites reference each other the most. And this is similar to like how academic citations are done. So like papers that get cited by other papers tend to be the most influential and like the most important. So this is an algorithm for quickly determining that using computers and linear algebra and eigenvectors and eigenvalues. So in this example, we have 4 pages, as I mentioned earlier, and they all reference each other. However, they reference each other for each a different amount. So for example, over here, I kind of drew it a little bit nicer. For example, like page 2 only references page 1, right? Now let's just look at this over here because it's a little bit simpler. So page 2 references, sorry, I made a mistake. Page 2 references page 3 and page 4. So, and page 1 references page 2 and page 3. Whereas page 3 references only page 1. So there's a lot of information and we have to store that somehow in a matrix because it's very confusing. And also, another thing, if I have a website and I start like referencing a million other websites, does that mean that I should have the same referencing power as one website that references another super influential website? I don't think so. So in this case, website number 3, right? That only references one website, so its weight is 1. Whereas website number 1, it references 3 websites, right? It references website number 2, it references website number 4, and it references website number 3. That means that the weight for each is 1/3. I apologize for the confusion caused by the thing on the left, but we're just going to be using this diagram from now on. So we need to figure out how to organize this in a matrix. So I created this over here, right? What this is it's a it's a matrix that shows that for page 1, it got 1/3 reference from page 2, 1/3 reference from page 3, 1/3 reference from page 4. Now for page 2, it got 1/2 reference from page 3, 1/2 reference from page 4, and etc. etc. So we need to figure out if we can get another matrix in the form of page 1, page 2, page 3, where we can turn this into a decimal, right? So basically, we want to multiply our matrix by another matrix. So we have our matrix A, and we want to multiply it by matrix X, where we kind of get the same, we get a result in which if you were to multiply it by A again, you would get X again. And this is because, like, for example, let's say we have a matrix in which they're all the same. So it's 0.25, 0.25, 0.25, 0.25, right? So they all have the same weighting, right? And we multiply this by our A, right? This is our weight of references. Now let's say we were to do this many different times, right? So the first time we do it, AV, you get this, right? Which is close. Now if you were to do it again, AV squared, you get something different. So the 0.37 from corresponding to reference to page number 1 becomes 0.43. The 0.08 corresponding to page 2 becomes 0.12. Now this means that the more times you do it, it starts to settle at an equilibrium. And if you keep on multiplying by A, you notice that like when you get to 8 to the power 6 and 8 to the power 7, A times 8 to the power 6 is 8 to the power 7. So essentially, when you multiply A by 8 to the power 6 x, basically, you're getting this, and it's the same. So in this way, it's an eigenvector. And you can notice how all of the elements in the column add up to 1. And this is important because, like, if it wasn't this way, then, okay, first of all, when you multiply, like, a vector like this by A, you should just get itself, because we want everything to be normalized in terms of 1. So we want our eigenvalue to be 1. So we want AX to be equal to 1 times X, which is just X, which is why all the elements in the column add up to 1. So as a result, you would get a matrix if you were to do this enough times um, in this type of form: 0.38, 0.12, 0.29, and 0.19. And you can, instead of just doing this by doing the calculation by multiplying by a repeatedly, you could simply just subtract a from I and find the determinant of that, which is um, and then you can find the eigenvector, which would be here. And in order to normalize it, you could divide it by the sum of all the columns. And this is useful because over here you can see how page 1 is being referenced the most, right? Because it's getting a reference from page 3, and page 3 isn't referencing anything else. So page 1 is clearly important. Whereas something like page 2, page 2 is not really getting a lot of references. It's the only thing it's getting is a 1/3 reference from page 1, so it's not as important. And this is how search engines like Google can use eigenvectors and eigenvalues to figure out which sites they should recommend and are most important. Of course, this is not the only thing that they use. They use other metrics because there's still ways to game this system. But this is a quick and easy way to use linear algebra, which can be quickly applied to programming, to order web pages. Thank you, and I hope you enjoyed and learned something from my presentation.